Okay, number 10 should have been labeled with a 13 in your review. It's just another composite function with domain, just to give you some extra practice. You don't have to worry about number 14 on your review. So this will be the last one. We're going to first compose f of g of x, which is my f of x function. So then we're going to substitute in a 2 over x in where the x used to be, because that's what g of x is, and g is going into f. And we need to clean this up. However, I'm going to pause for a second and work off to the side here. I'm going to pause cleaning that up and work off to the side and find my domain. The domain of a composite function is the domain of your new function and any restrictions that come along from g of x. So I'm looking at my new function here, the unsimplified version, and I see I have a fraction bar. And whenever you have a fraction bar, you take what's underneath and you set that whole thing equal to 0. Okay, anything under a fraction bar, take the whole expression, set it equal to 0, solve it. I get 2 over x is equal to negative 1. I'm going to multiply both sides by x, or if you want, you can make this a proportion if that's helps you solve it a little bit easier. And I get negative 1x is equal to 2, divide both sides by negative 1, I get x is equal to negative 2. Technically, that is what x cannot equal because it makes a 0 in the denominator. And that takes care of the domain of my composite function. But we also need to look at the inner functions domain right here. There's another fraction bar in the problem, so every time you have a fraction, you need to take that denominator and set it equal to 0. So the x that was under the fraction bar for g of x must also be set equal to 0. And then set that denominator equal to 0, and guess what? It's already solved for. There's nothing to calculate, and x cannot equal 0. So your final domain is that you can have negative 2 and you can have 0. And so we'll put open circles on our number line, shade, shade, shade everywhere else. And our final domain goes from negative infinity up to negative 2, unioned with negative 2 to 0, unioned with 0 to infinity. And now for the cleanup. I'm going to show you a different method to clean this up. I'll show you Mr. Manning's method. Okay, so it took away the parentheses, and that's what I have. What Mr. Manning does is just multiply everything by x. If you, let me get rid of this in my way. If you multiply a fraction by any version of a 1, and in this case x over x is 1, then it's a legal move. So I'm going to distribute now and multiply straight across, and I get x times 3, which is 3x, and on the bottom I'm going to end up with x times 2 over x plus 1. I haven't distributed yet, but I'm going to distribute now, and I get 3x over 2x over x plus x. So I just distributed that x straight through, and then the x's will cancel right there, and I get 3x over 2 plus x. And this is the answer that I would get if I would have done the process the way I've been doing them for you, by combining these two red fractions together. Actually, one isn't a fraction yet, but by combining these two fractions together, you would, and inverting and multiplying and doing everything we did in class, and you would still get the same answer right here. So you get to take your pick on which way you want to clean it up, whatever math skills that you are comfortable with to get that answer. Go ahead and get it. On your test, it won't be that complicated. It'll be more straightforward, and you won't have such a cleanup to do. But anyway, the domain is the big idea or big deal here. When you find the domain of a composite function, you want the domain of the new function you create. Just find its domain And then any little extra restrictions that come from that inner function, you need to bring those along. So my inner function was 2 over x. I had an x in the denominator. I had to set it greater than equal to 0 and bring that into my final domain.